Our galaxy, the Milky Way, is one of potentially hundreds of millions of galaxies in the vast expanse of the universe. This staggering fact raises profound questions about the formation and existence of galaxies. Galaxies are enormous systems comprised of stars, stellar remnants, interstellar gas, dust, and dark matter, all bound together by gravity. The processes that led to the formation of galaxies are still subjects of intense study and debate. Scientists believe that galaxies formed from density fluctuations in the early universe, where regions of higher density gradually attracted more matter through gravitational attraction, eventually leading to the formation of stars and galaxies. These galactic structures are not just random collections of matter, they follow specific patterns and exhibit intricate dynamics, driven by the underlying laws of physics. One of the most fundamental questions in cosmology is how galaxies, like our Milky Way, came to exist. The Milky Way itself is a barred spiral galaxy containing billions of stars, with our solar system located on one of its spiral arms. The formation of galaxies began shortly after the Big Bang, when the universe was filled with a hot, dense plasma. As the universe expanded and cooled, this plasma began to form neutral atoms, and regions with slightly higher density started to collapse under their own gravity, forming the first stars and galaxies. The exact mechanisms of this process involve complex interactions between gravity, gas dynamics, and dark matter. The Big Bang, which occurred approximately 13.8 billion years ago, marks the inception of the universe. This event was not an explosion in the traditional sense, but rather an expansion of space itself. At the moment of the Big Bang, the universe was in an extremely hot and dense state, and it has been expanding ever since. This expansion explains why galaxies are moving away from each other, a phenomenon observed through the redshift of their light. As the universe expanded, it cooled, allowing the formation of subatomic particles and eventually simple atoms. Over time, these atoms coalesced to form stars and galaxies. The concept of the Big Bang is supported by multiple lines of evidence, including the cosmic microwave background radiation, and the distribution of galaxies in the universe. The Big Bang theory is a cornerstone of modern cosmology. It describes how the universe expanded from a highly compressed state to its current vast expanse. The initial conditions of the universe, just moments after the Big Bang, were incredibly extreme, with temperatures reaching billions of degrees. In these conditions, fundamental particles such as quarks and gluons existed in a quark-gluon plasma. Ordinary matter, which includes everything we can see and touch, constitutes only 5% of the universe's total mass and energy. The remaining 95% consists of mysterious substances known as dark matter and dark energy. Dark matter, which makes up about 27% of the universe, does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. It plays a crucial role in the formation and structure of galaxies, acting as a sort of cosmic scaffold that holds galaxies together. Without dark matter, galaxies would not have enough gravitational pull to stay intact and would disperse. The concept of dark matter was first proposed to explain discrepancies between the observed rotation curves of galaxies and the predictions made by Newtonian mechanics. Observations showed that stars in the outer regions of galaxies were moving faster than could be accounted for by the visible matter alone. This led scientists to conclude that there must be additional, unseen mass exerting gravitational influence, which we now call dark matter. Dark matter interacts primarily through gravity, and its exact nature remains one of the biggest mysteries in astrophysics. Various candidates for dark matter have been proposed, including weakly interacting massive particles, WIMPs, and axions, but none have been definitively detected. Dark energy is one of the most profound mysteries in modern cosmology, constituting about 68% of the universe's total energy content. Unlike matter and radiation, which interact with each other through forces such as gravity and electromagnetism, dark energy operates in a way that defies conventional understanding. It is not directly observable, yet its effects are evident in the accelerated expansion of the universe. Discovered relatively recently in the late 1990s, dark energy continues to challenge physicists and astronomers, reshaping our understanding of the cosmos and its ultimate destiny. The story of dark energy begins with the observation of distant supernovae, which served as standard candles to measure the expansion of the universe. These observations, conducted independently by two teams of researchers, the Supernova Cosmology Project and the High-Z Supernova Search Team, revealed that the universe's expansion was not slowing down due to gravity, as previously assumed. Instead, it was accelerating. This unexpected result indicated the presence of a repulsive force or energy that counteracts gravity on cosmic scales. The term dark energy was coined to describe this mysterious phenomenon. One of the defining characteristics of dark energy is its uniformity. Unlike matter, which clusters into stars, galaxies, and other structures, dark energy appears to be evenly distributed throughout space. This property aligns with the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. The uniform nature of dark energy ensures that its effects are felt universally, influencing the dynamics of the cosmos regardless of location. Dark energy is often associated with the concept of the cosmological constant, lambda, introduced by Albert Einstein in 1917 as a modification to his equations of general relativity. At the time, Einstein believed the universe was static and unchanging, so he added the cosmological constant to counteract the attractive force of gravity and maintain a stable universe. When Edwin Hubble later discovered that the universe was expanding, Einstein abandoned the cosmological constant, famously calling it his greatest blunder. However, the discovery of accelerated expansion in the 1990s revived interest in the cosmological constant as a possible explanation for dark energy. In the cosmological constant model, dark energy is described as a constant energy density that permeates space. This interpretation aligns with observations and provides a simple explanation for the universe's accelerated expansion. However, it raises a significant theoretical problem known as the cosmological constant problem. The energy density associated with the cosmological constant, as predicted by quantum field theory, is vastly larger than the value inferred from observations. This discrepancy, spanning many orders of magnitude, highlights the limitations of our current understanding and suggests the need for new physics. Beyond the cosmological constant, alternative theories have been proposed to explain dark energy. One such theory involves dynamic fields, collectively known as quintessence, which evolve over time and contribute to the universe's accelerated expansion. Unlike the cosmological constant, quintessence models allow for a varying energy density, which could change the behavior of dark energy over cosmic time. These models introduce new parameters and mechanisms, offering greater flexibility but also requiring additional observational evidence to confirm their validity. Another avenue of exploration involves modifications to general relativity. Some theories suggest that dark energy arises from deviations in the behavior of gravity on large scales. These modifications, often categorized under modified gravity theories, aim to unify the effects of dark energy with the fundamental forces of nature. Examples include theories based on extra dimensions, brane world scenarios, and extensions of general relativity such as FR gravity. These approaches provide intriguing alternatives but also face challenges in maintaining consistency with existing observations and experiments. Dark energy plays a crucial role in shaping the universe's ultimate fate. In the current cosmological model, known as lambda CDM, lambda cold dark matter, the universe consists of dark energy, dark matter, and ordinary matter. Dark energy dominates the total energy content, driving the accelerated expansion observed today. If this expansion continues indefinitely, the universe could approach a scenario known as the Big Freeze. In this scenario, galaxies would drift increasingly far apart, and star formation would gradually cease as available gas is exhausted. Over trillions of years, stars would burn out, leaving a cold and dark cosmos devoid of light and heat. Alternatively, if dark energy's properties change over time, other outcomes are possible. For example, in a Big Rip scenario, dark energy's repulsive force could grow stronger, eventually overcoming all other forces. In this case, the expansion of the universe would accelerate to the point where galaxies, stars, planets, and even atomic particles are torn apart. Conversely, if dark energy diminishes or reverses its effects, the universe could undergo a big crunch, collapsing back into a hot, dense state. These scenarios highlight the importance of understanding dark energy's nature and behavior. Observational efforts to study dark energy rely on multiple techniques, each providing complementary insights. Measurements of the cosmic microwave background, CMB, the faint afterglow of the Big Bang, reveal the universe's geometry and composition. Large-scale galaxy surveys map the distribution of galaxies, tracing the underlying structure of the universe and its evolution. Observations of baryon acoustic oscillations, BAOs, imprints of sound waves from the early universe, serve as standard rulers for measuring cosmic distances. Additionally, gravitational lensing, the bending of light by massive objects, offers a means to probe dark energy's effects on the growth of cosmic structures. The discovery of dark energy has profound implications for fundamental physics and cosmology. It challenges our understanding of the universe's basic constituents and forces, prompting the development of new theories and experimental approaches. Dark energy's existence suggests that our current models of particle physics and gravity are incomplete, requiring extensions or unifications that account for its effects. Moreover, dark energy provides a natural context for addressing philosophical questions about the universe's origin, structure, and purpose. Despite significant progress, dark energy remains one of the greatest enigmas in science. Its detection and characterization require innovative technologies and collaborative efforts on a global scale. Projects such as the Dark Energy Survey, DES, the Euclid mission, and the Vera C. Rubin Observatory aim to refine our measurements of cosmic acceleration, and uncover clues about dark energy's nature. These endeavors exemplify the spirit of scientific inquiry, uniting researchers across disciplines to tackle one of the universe's most profound mysteries. The discovery of dark energy was one of the most surprising findings in modern cosmology. When astronomers measured the brightness of distant Type Ia supernovae, they found that these supernovae were farther away than expected, indicating that the expansion of the universe was accelerating. This discovery led to the realization that a new form of energy, which we now call dark energy, must be driving this acceleration. The exact nature of dark energy is unknown, but it is thought to be related to the vacuum energy of space itself, as predicted by quantum field theory. Understanding dark energy is a major goal of modern cosmology, as it has profound implications for the ultimate fate of the universe. The CMB is often referred to as the afterglow of the Big Bang. It provides a direct window into the conditions of the early universe, just a few 100,000 years after its inception. The uniformity of the CMB across the sky, with only small fluctuations, supports the idea that the universe was once in a hot, dense state. These fluctuations, or anisotropies, in the CMB are tiny variations in temperature that reflect the initial density perturbations that would eventually grow into galaxies and large-scale structures. Detailed measurements of the CMB, such as those made by the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have provided invaluable data for testing cosmological models and refining our understanding of the universe's composition and evolution. The redshift of galaxies is another key observation supporting the Big Bang theory, and the ongoing expansion of the universe. When we observe distant galaxies, their light is shifted towards the red end of the spectrum, a phenomenon known as redshift. This shift occurs because the galaxies are moving away from us, stretching the wavelength of the light they emit. The greater the distance, the faster the galaxies are receding, which is described by Hubble's law. This observation not only confirms that the universe is expanding but also allows scientists to estimate the rate of expansion and thereby infer the universe's age. Edwin Hubble's discovery of the relationship between the distance of galaxies and their redshift was a pivotal moment in cosmology. Hubble's law states that the velocity at which a galaxy is receding from us is proportional to its distance. By measuring the redshift and distances of galaxies, astronomers can determine the value of the Hubble constant, which provides a measure of the rate of expansion of the universe. The current value of the Hubble constant is approximately 73 km per second per megaparsec, though there is still some debate and uncertainty in this measurement. The redshift of light from distant galaxies also provides insights into the dynamics of the universe's expansion. In an expanding universe, the wavelength of light is stretched as space itself expands. This means that the light we observe from distant galaxies has been redshifted, or stretched, to longer wavelengths. The degree of redshift increases with distance, indicating that the farther away a galaxy is, the faster it is moving away from us. This observation supports the idea that the universe has been expanding since the Big Bang and continues to do so. Understanding the vastness and complexity of the universe involves a multidisciplinary approach, incorporating observations, theoretical models, and advanced technologies. As we continue to explore and study the cosmos, new discoveries will undoubtedly deepen our understanding of the universe's origins, its current state, and its ultimate fate. The quest to unravel the mysteries of the universe is a testament to human curiosity and the relentless pursuit of knowledge. Each piece of evidence, from the cosmic Within the first second after the Big Bang, the universe underwent significant transformations that set the stage for its structure and evolution. During this incredibly brief period, the fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, began to separate. Initially, these forces were unified in a single superforce. As the universe expanded and cooled, this symmetry broke, leading to the distinct forces we observe today. This separation of forces was crucial in shaping the interactions and behaviors of particles that would form the building blocks of matter. In the first moments after the Big Bang, the universe was in a state of extreme temperature and density. It consisted of a hot, dense plasma of fundamental particles such as quarks, gluons, and leptons. The energy levels were so high that the fundamental forces of nature were unified. However, as the universe expanded and cooled, these forces began to distinguish themselves, a process known as symmetry breaking. This transition set the stage for the subsequent formation of complex structures in the universe. One of the critical processes during the early universe was baryogenesis, which occurred within the first few seconds. During baryogenesis, quarks combined to form protons and neutrons, the building blocks of atomic nuclei. This process was influenced by the imbalance between matter and antimatter, leading to a slight excess of matter over antimatter, which is why our universe is composed primarily of matter. Understanding baryogenesis is essential for explaining why the universe is dominated by matter rather than antimatter. The exact mechanisms of baryogenesis involve complex interactions and remain an area of active research in theoretical physics. The formation of protons and neutrons was a crucial step in the evolution of the universe. These particles are collectively known as baryons, and their creation set the stage for the formation of atomic nuclei. The interactions involving the weak nuclear force and possible violations of fundamental symmetries in particle physics played a significant role in this process. The observed matter-antimatter asymmetry, where there is more matter than antimatter, remains one of the biggest mysteries in cosmology. Various theories and experiments aim to uncover the details of baryogenesis to understand this crucial aspect of the universe's history. A pivotal event in the early universe was cosmic inflation, a period of extremely rapid expansion that occurred within a tiny fraction of a second after the Big Bang. During inflation, the universe expanded exponentially, increasing in size by a factor of at least 10 to the power of 26 in a fraction of a second. This dramatic expansion smoothed out any initial irregularities in the energy distribution, leading to the highly uniform and isotropic universe we observe today. Cosmic inflation also amplified quantum fluctuations, which later evolved into the large-scale structures such as galaxies and galaxy clusters. The theory of cosmic inflation was proposed in the early 1980s by physicists such as Alan Guth and Andrei Linde. It addresses several key issues in cosmology, such as the horizon problem, which questions why the universe appears uniform in all directions despite regions being causally disconnected. Inflation also explains the flatness problem, which refers to the observed spatial flatness of the universe. By exponentially increasing the size of the universe, inflation stretches out any initial curvature, resulting in the nearly flat geometry we observe today. During inflation, the energy density of the universe was dominated by a hypothetical field known as the inflation field. The dynamics of this field drove the rapid expansion, and its decay led to the reheating of the universe, filling it with particles and radiation. The tiny quantum fluctuations in the inflation field were stretched to macroscopic scales during inflation, seeding the density variations that eventually grew into galaxies and clusters of galaxies. These fluctuations are imprinted in the cosmic microwave background, CMB, as small temperature anisotropies, providing a window into the conditions of the early universe. Following the period of cosmic inflation, the universe continued to expand and cool. As it cooled, particles began to combine to form neutral atoms, a process known as recombination. The universe had cooled sufficiently for electrons to combine with protons and form hydrogen atoms. This process released photons, resulting in the decoupling of matter and radiation. These photons have traveled through space ever since and are observed today as the cosmic microwave background, CMB, radiation. The CMB provides a snapshot of the universe at this early stage and contains valuable information about its composition and structure. The formation of neutral atoms during recombination allowed the universe to become transparent to radiation. Before recombination, the universe was a hot, opaque plasma where photons were constantly scattered by free electrons. As electrons combined with protons to form hydrogen atoms, photons could travel freely, creating the CMB. The CMB is a nearly uniform background of microwave radiation with a temperature of approximately 2.7 Kelvin, but it contains slight anisotropies that reflect the density fluctuations in the early universe. These anisotropies provide critical insights into the initial conditions and subsequent evolution of the universe. The cooling of the universe also allowed for the formation of hydrogen and helium, the simplest and most abundant elements. These elements formed during a period known as Big Bang nucleosynthesis, which occurred within the first few minutes after the Big Bang. During nucleosynthesis, protons and neutrons combined to form the nuclei of these light elements. The relative abundances of hydrogen and helium observed in the universe today closely match the predictions of Big Bang nucleosynthesis, providing strong evidence for the Big Bang theory. Hydrogen is the most abundant element in the universe, making up approximately 75% of its elemental mass, while helium accounts for about 24%. Heavier elements, such as carbon and oxygen, were formed later in the interiors of stars, through the process of stellar nucleosynthesis. The initial abundances of hydrogen and helium played a crucial role in the formation of the first stars and galaxies. These early stars, known as population 3 stars, were composed almost entirely of hydrogen and helium and were responsible for creating the first heavy elements, through nuclear fusion. Big Bang nucleosynthesis occurred when the universe was between 10 seconds and 20 minutes old, during a period when temperatures were high enough for nuclear reactions to occur. The process began with the formation of deuterium, a heavy isotope of hydrogen, followed by the fusion of deuterium nuclei to form helium-4. Trace amounts of other light elements, such as lithium and beryllium, were also produced. The predicted ratios of these elements, based on nuclear physics and the conditions of the early universe, are in excellent agreement with observations, providing a strong confirmation of the Big Bang model. The early universe underwent a series of transformative events within the first seconds and minutes after the Big Bang. The separation of fundamental forces set the stage for the universe's structure, while baryogenesis led to the formation of protons and neutrons. Cosmic inflation caused the universe to expand exponentially, smoothing out energy distribution and laying the groundwork for large-scale structures. As the universe cooled, hydrogen and helium, the simplest and most abundant elements, formed, paving the way for the development of stars and galaxies. These processes and events collectively shaped the universe we observe today and continue to be subjects of intense scientific study and exploration. Understanding the early universe involves a multidisciplinary approach, incorporating observations, theoretical models, and advanced technologies. The interplay between fundamental forces, particle interactions, and cosmic inflation created the conditions necessary for the formation of matter and the large-scale structure of the universe. As we continue to explore and study the cosmos, new discoveries will undoubtedly deepen our understanding of the early universe and its evolution. The quest to unravel the mysteries of the early universe is a testament to human curiosity and the relentless pursuit of knowledge. Each piece of evidence, from the cosmic microwave background radiation to the abundance of light elements, helps us reconstruct the universe's history and gain insights into its future. The epoch of recombination, occurring around 378,000 years after the Big Bang, was one of the most crucial periods in cosmic history. Prior to this epoch, the universe was a hot, dense plasma of photons, electrons, and protons. Because the universe was so hot and dense, photons constantly scattered off free electrons, a process known as Thomson scattering. This scattering made the universe opaque, much like fog obscures visibility on a humid morning. However, as the universe expanded, it cooled, and when the temperature dropped to around 3000 Kelvin, conditions became favorable for recombination to occur. During recombination, free electrons combined with protons to form neutral hydrogen atoms, significantly changing the universe's characteristics. This transition to a neutral state allowed photons to travel freely for the first time, leading to the decoupling of matter and radiation. The release of these photons is observed today as the cosmic microwave background, CMB, radiation, which provides a baby picture of the universe at the time of recombination. The CMB is nearly uniform in all directions, with slight variations that correspond to density fluctuations. These variations are critical as they represent the seeds of all current structures in the universe, such as galaxies and clusters of galaxies. Before recombination, the universe was dominated by a hot plasma where photons were constantly interacting with free electrons. This state is similar to the interior of stars where high temperatures keep matter ionized. However, as the universe expanded, it cooled, allowing electrons and protons to combine and form neutral hydrogen. This recombination significantly decreased the scattering of photons, allowing them to travel freely and making the universe transparent for the first time. This transparency is what we observe today in the form of the CMB, a relic radiation that carries information about the early universe's conditions. Recombination is a pivotal event in the history of the universe, marking a transition from one state of existence to another. To fully appreciate its importance, one must delve into the physics of the early universe and understand the consequences of this phenomenon for the formation of the structures we observe today. This essay explores recombination in detail, examining its role in shaping the cosmos over a 1000-word narrative. Shortly after the Big Bang, the universe was an incredibly hot and dense environment. In this primordial era, temperatures were so high that atoms could not exist. Instead, the universe was filled with a plasma, a soup of protons, neutrons, electrons, and photons. The intense energy of this plasma prevented electrons from binding to nuclei, as any nascent atom would be quickly ionized by high-energy photons. This period is often referred to as the photon-baryon fluid phase because photons and baryons, protons and neutrons, interacted strongly, creating a tightly coupled medium. In this plasma state, photons constantly scattered off free electrons through Thomson scattering, making the universe opaque. Light could not travel far before being absorbed and re-emitted, meaning that information about the early universe was effectively trapped within this dense fog. This opaque plasma persisted for hundreds of thousands of years as the universe expanded and cooled. Recombination refers to the epoch, approximately 380,000 years after the Big Bang, when the universe cooled sufficiently for protons and electrons to combine and form neutral hydrogen atoms. The term recombination might be misleading, as it suggests that atoms existed before and were reformed. However, this was the first time neutral atoms formed in the universe. The immediate consequence of recombination was the decoupling of photons from matter. Before recombination, photons were constantly interacting with free electrons, but with the formation of neutral hydrogen, the number of free electrons dropped dramatically. This reduction in scattering allowed photons to travel freely through space for the first time. These freely traveling photons form the cosmic microwave background, CMB, a relic radiation that provides a snapshot of the universe at the moment of decoupling. The transparency of the universe following recombination is crucial for our understanding of cosmology. The CMB carries imprints of the density fluctuations and temperature variations in the early universe, which are the seeds of all cosmic structure. Observations of the CMB have provided invaluable insights into the composition, age, and evolution of the cosmos. While the universe becoming transparent is a significant milestone, the importance of recombination extends far beyond this aspect. Recombination marked the end of the plasma era, and the beginning of the era when structures could form. Neutral hydrogen atoms played a critical role in the cooling processes that enabled gas clouds to collapse under the influence of gravity, leading to the formation of the first stars and galaxies. Before recombination, the intense interactions between photons and matter prevented significant gravitational collapse. Radiation pressure counteracted gravitational forces, keeping matter from clumping together. However, once neutral hydrogen formed, this radiation pressure diminished, allowing gravity to dominate. Neutral hydrogen atoms also facilitated cooling mechanisms necessary for star formation. As gas clouds collapsed, they heated up due to gravitational energy conversion. For stars to form, these gas clouds needed to lose energy and cool down. Neutral hydrogen provided a means for this cooling through processes like collisional excitation and the subsequent emission of photons. Without recombination and the resultant neutral hydrogen, these cooling processes would not have occurred, and the formation of stars and galaxies would have been severely impeded. Recombination ushered in the so-called cosmic dark ages, a period between the release of the CMB and the formation of the first stars. During this time, the universe was filled with neutral hydrogen, and was dark because no luminous objects existed yet. However, the groundwork for the formation of the first stars was laid during this era. Small density fluctuations in the distribution of matter, imprinted during the inflationary epoch, began to grow under the influence of gravity. Over time, regions of slightly higher density attracted more matter, leading to the formation of the first gravitationally bound structures. These dense regions eventually gave rise to the first stars, which illuminated the universe and ended the cosmic dark ages. The first stars, known as population 3 stars, were massive and short-lived. They played a vital role in reionizing the universe, marking another significant transition in cosmic history. The ultraviolet radiation from these stars ionized the surrounding neutral hydrogen, creating ionized bubbles that eventually merged, transforming the universe into its current ionized state. This reionization era would not have been possible without the initial recombination event that allowed the first stars to form. Recombination is a cornerstone of modern cosmology and astrophysics. The study of the CMB, which originated at the time of recombination, has become one of the most powerful tools for understanding the universe. The temperature fluctuations and polarization patterns in the CMB provide direct evidence for the physics of the early universe, including the processes of inflation, baryon acoustic oscillations, and the distribution of dark matter. Recombination also underscores the interplay between fundamental forces and particles in shaping the universe. It highlights the delicate balance between radiation, matter, and gravity, and how small changes in these interactions could have led to a vastly different cosmos. For instance, if the universe had not cooled sufficiently for recombination to occur, the persistent plasma state would have precluded the formation of stars, galaxies, and ultimately, life as we know it. Recombination is much more than a transition from opacity to transparency. It represents a fundamental turning point in the history of the universe, enabling the formation of the first stars and galaxies and setting the stage for the complex cosmic web we observe today. By allowing photons to decouple from matter, recombination not only gave us the cosmic microwave background but also created the conditions necessary for structure formation. The importance of recombination resonates across cosmology, astrophysics, and our understanding of the universe's evolution. It highlights how seemingly small changes in the early universe had profound consequences, shaping the cosmos into the rich tapestry of galaxies, stars, and planets we see today. Without recombination, the universe would have remained a hot, opaque plasma, devoid of the intricate structures and phenomena that define our cosmic existence. A critical aspect of the early universe was the role of molecular hydrogen, H2, in the cooling of gas clouds. Molecular hydrogen is the simplest and most abundant molecule in the universe, consisting of two hydrogen atoms bonded together. It played a pivotal role in cooling gas clouds, enabling the formation of the first stars. After recombination, the universe was predominantly filled with neutral hydrogen and helium. For these gas clouds to collapse and form stars, they needed to cool down, and molecular hydrogen was the most efficient coolant available. When gas clouds cool, they lose thermal pressure, allowing gravity to dominate and cause the clouds to collapse. The cooling process involves the emission of radiation, and molecular hydrogen, being a simple and abundant molecule, was very effective at radiating away energy, thus facilitating the collapse of gas clouds. The efficiency of molecular hydrogen as a coolant is due to its ability to emit radiation when it undergoes rotational and vibrational transitions. These emissions allow the gas to lose energy and cool down, making it possible for gravitational forces to initiate the collapse of gas clouds. The formation of molecular hydrogen was a key step in the evolution of the universe. It allowed the gas clouds to reach the critical densities required for star formation. The first stars, known as population 3 stars, formed from these cooled gas clouds. These stars were massive, with some estimates suggesting they could have been hundreds of times the mass of the Sun. Population 3 stars had very short lifespans due to their massive size, and they burned through their nuclear fuel rapidly. They ended their lives in spectacular supernova explosions, dispersing newly formed heavier elements into the surrounding interstellar medium. The synthesis of heavier elements in stars and their subsequent distribution into space was a fundamental process that enriched the universe's chemical composition. During their lifetimes, stars undergo nuclear fusion in their cores, converting lighter elements like hydrogen and helium into heavier elements such as carbon, oxygen, and iron. The most massive stars end their lives in supernova explosions, which are powerful enough to produce even heavier elements and scatter them into the interstellar medium. This process, known as nucleosynthesis, enriched the universe with the elements necessary for the formation of planets and life. As these first-generation stars went supernova, they created shock waves that compressed nearby gas clouds, triggering the formation of new stars. This second generation of stars, known as population 2 stars, formed from gas clouds that contain some heavier elements, or metals, produced by the previous generation of stars. These stars were less massive and had longer lifespans than population 3 stars. Population 2 stars continued the process of nucleosynthesis, further enriching the interstellar medium with heavy elements. The gradual enrichment of the universe's chemical composition continued with the formation of population I stars, like our Sun. These stars formed from gas clouds that were even more enriched with heavy elements, thanks to the contributions of previous generations of stars. Population I stars have the highest metal content, and are typically found in the spiral arms of galaxies. The presence of heavier elements in these stars facilitated the formation of planets, including rocky planets like Earth. Elements such as carbon, nitrogen, oxygen, and phosphorus are fundamental building blocks of biological molecules, and their availability in the right proportions is essential for the emergence of life. The formation of planets and the potential for life depend on a delicate interplay of astrophysical processes. The heavy elements synthesized in stars are dispersed into the interstellar medium through supernova explosions and stellar winds. These elements are then incorporated into new generations of stars and planetary systems. The presence of heavy elements in protoplanetary disks around young stars allows for the formation of solid planetesimals, which can coalesce to form planets. The availability of water, organic molecules, and other life-essential compounds in these environments creates the potential for the development of life. The formation of planets involves the aggregation of dust and gas in protoplanetary disks around young stars. These disks are composed of material that has been enriched with heavy elements from previous generations of stars. Small particles of dust stick together through electrostatic forces, gradually forming larger bodies known as planetesimals. As these planetesimals collide and merge, they form protoplanets, which continue to grow by accreting additional material. The presence of heavy elements in these disks allows for the formation of rocky planets, and other complex structures. The potential for life on planets is influenced by the chemical composition of their environments. The presence of water, carbon-based molecules, and other essential compounds creates the conditions necessary for life as we know it. The synthesis of these compounds is facilitated by the availability of heavy elements produced by stellar nucleosynthesis. For example, carbon is a key element in the formation of complex organic molecules, while oxygen is essential for the formation of water. The presence of these elements in the right proportions is crucial for the development of life. Understanding the early universe involves a multidisciplinary approach, incorporating observations, theoretical models, and advanced technologies. The interplay between fundamental forces, particle interactions, and cosmic inflation created the conditions necessary for the formation of matter and the large-scale structure of the universe. As we continue to explore and study the cosmos, new discoveries will undoubtedly The cosmic microwave background, CMB, is one of the most significant and awe-inspiring discoveries in the field of cosmology. Its presence offers an unparalleled window into the early universe, revealing critical insights about its origins, structure, and evolution. Discovered serendipitously in 1965 by Arno Penzias and Robert Wilson, the CMB is often referred to as the afterglow of the Big Bang. This faint glow of radiation has not only confirmed the Big Bang theory as the leading explanation for the universe's creation, but has also revolutionized our understanding of the cosmos. The CMB represents a snapshot of the universe when it was approximately 380,000 years old, a period that is minuscule in the context of the universe's current age of 13.8 billion years. This specific moment in cosmic history corresponds to an event known as recombination. Before recombination, the universe was an extremely hot and dense plasma, consisting primarily of protons, electrons, and photons. In this state, photons were constantly scattered by free electrons, preventing them from traveling any significant distance. As the universe expanded, it cooled, eventually reaching a temperature of about 3000 Kelvin. At this critical juncture, protons and electrons combined to form neutral hydrogen atoms, significantly reducing the scattering of photons. This decoupling of matter and radiation allowed photons to travel freely for the first time, effectively releasing the light that we now observe as the CMB. The discovery of the CMB was accidental yet transformative. Penzias and Wilson, while working at Bell Telephone Laboratories, were conducting experiments with a highly sensitive radio antenna. They detected a persistent and inexplicable noise that seemed to originate uniformly from all directions in the sky. Initially, they suspected various earthly sources, including equipment malfunctions and even pigeon droppings on the antenna. However, upon consulting with theoretical physicists Robert Dicke and Jim Peebles, they realized that their observation matched the predictions of a remnant radiation from the Big Bang, as theorized by George Gamow, Ralph Alpha, and Robert Herman decades earlier. The CMB is remarkably uniform across the sky, with a temperature of approximately 2.7 Kelvin, just above absolute zero. However, it is not perfectly uniform. Tiny fluctuations in temperature and density, on the order of 1 part in 100,000, are imprinted in the CMB. These small anisotropies hold immense significance, as they reflect the primordial density variations in the early universe. Over billions of years, these initial irregularities served as the seeds for the formation of large-scale cosmic structures such as galaxies, clusters, and superclusters. Regions with slightly higher density attracted more matter due to gravitational pull, eventually growing into the structures we observe today. The study of the CMB has advanced significantly since its discovery. Detailed observations have been made by ground-based telescopes, balloon experiments, and space missions. Notable among these are the Cosmic Background Explorer, COB, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite. These missions have provided increasingly precise measurements of the CMB's temperature fluctuations, polarization, and power spectrum, enabling scientists to infer key cosmological parameters with remarkable accuracy. COBE, launched by NASA in 1989, was the first satellite to measure the CMB's anisotropies. It confirmed the CMB's blackbody spectrum, as predicted by the Big Bang theory, and detected temperature variations across the sky. WMAP, operational from 2001 to 2010, refined these measurements, producing a detailed map of the temperature fluctuations and yielding critical insights into the universe's composition and geometry. Finally, the European Space Agency's Planck satellite, launched in 2009, provided the most detailed and precise measurements of the CMB to date, further constraining cosmological models and parameters. One of the most important aspects of the CMB is its role in determining the universe's composition. The detailed analysis of the CMB's power spectrum has revealed that the universe consists of approximately 68% dark energy, 27% dark matter, and only 5% ordinary matter. This composition underscores the dominance of mysterious and poorly understood components in shaping the cosmos. Additionally, the CMB provides strong evidence for the inflationary model of the early universe, which posits a brief period of exponential expansion shortly after the Big Bang. Inflation explains the observed homogeneity and isotropy of the CMB, as well as the distribution of large-scale structures in the universe. The polarization of the CMB is another critical area of study. As photons interacted with free electrons during the era of recombination, a specific pattern of polarization was imprinted in the CMB. This polarization carries information about the universe's early conditions and the presence of primordial gravitational waves. Detecting these gravitational waves through CMB polarization would provide direct evidence for inflation and deepen our understanding of the universe's origins. Efforts to measure these subtle signals are ongoing, with experiments such as BICEP and the South Pole Telescope playing a leading role. The CMB also serves as a cosmic time capsule, preserving information about the universe's earliest moments. By studying the CMB, scientists can probe conditions mere fractions of a second after the Big Bang. This capability has transformed the CMB into a cornerstone of modern cosmology, enabling researchers to test theoretical models and refine their understanding of fundamental physics. For example, discrepancies between the observed and predicted values of certain cosmological parameters, such as the Hubble constant, have sparked debates about the need for new physics or adjustments to existing models. The implications of the CMB extend beyond cosmology. Its discovery and study have fostered interdisciplinary collaborations, bringing together astrophysicists, particle physicists, and theorists to tackle some of the most profound questions about the universe. Moreover, the CMB's existence underscores the interconnectedness of cosmic phenomena, linking the physics of the early universe to the large-scale structures we observe today. Despite its immense success, the study of the CMB is not without challenges. Observational data must be meticulously corrected for foreground contamination, such as emissions from the Milky Way's interstellar medium, and extragalactic sources. Additionally, distinguishing the subtle signals of primordial gravitational waves from other effects requires extraordinary precision and innovative techniques. These challenges, however, have spurred the development of cutting-edge technologies and methodologies, driving progress in both cosmology and observational astronomy. The future of CMB research holds great promise. Upcoming missions and experiments aim to achieve even greater sensitivity and resolution, unlocking new levels of detail about the universe's earliest moments. Projects such as the Lightbird satellite and the Simons Observatory are poised to make significant contributions, particularly in the quest to detect primordial gravitational waves. These efforts will complement other observational strategies, such as galaxy surveys and gravitational wave detectors, creating a comprehensive picture of the universe's history and evolution. The CMB's profound significance lies in its ability to connect the past, present, and future of the cosmos. It serves as a bridge between the universe's fiery origins and its current state, revealing the processes that have shaped its development over billions of years. By studying the CMB, we not only deepen our understanding of the universe's past but also gain insights into its ultimate fate. Whether the universe will continue expanding indefinitely, collapse in a big crunch, or undergo some other transformation remains an open question, but the CMB provides critical clues to unraveling this mystery. The cosmic microwave background is a cornerstone of modern cosmology, offering an unparalleled glimpse into the early universe. From its accidental discovery to its role in shaping our understanding of the cosmos, the CMB has transformed the field, enabling precise measurements of fundamental parameters and testing theoretical models. Its study continues to inspire and challenge scientists, driving advancements in technology and expanding the boundaries of human knowledge. As we explore the mysteries of the CMB, we uncover not only the story of the universe's beginnings but also our place within the grand cosmic tapestry. The precision with which the CMB has been studied over the decades has yielded remarkable results. Observations by missions such as the COBE, Cosmic Background Explorer, in the 1990s, WMAP, Wilkinson Microwave Anisotropy Probe, in the 2000s, and Planck Satellite in the 2010s have refined our understanding of the universe's fundamental properties. By analyzing the CMB's spectrum and its fluctuations, scientists have determined that the universe is approximately 13.8 billion years old. This precision is remarkable given the immense timescales involved and highlights the power of modern astrophysical techniques. Moreover, the CMB has provided a clear picture of the universe's composition. It confirms that ordinary matter, comprising atoms, stars, and planets, accounts for only 5% of the universe's total energy density. The remainder consists of 25% dark matter, a mysterious substance that interacts gravitationally but not electromagnetically, and 70% dark energy, an enigmatic force driving the accelerated expansion of the universe. These proportions, derived from the detailed analysis of the CMB, align closely with independent observations of galaxy distributions, supernovae, and gravitational lensing. The study of the CMB has also provided critical tests for the Big Bang theory, cementing it as the prevailing model for the universe's origin. The nearly perfect blackbody spectrum of the CMB matches predictions of the Big Bang model, demonstrating that the universe has cooled from an intensely hot and dense state to its current, cooler state over billions of years. Additionally, the uniformity of the CMB across vast regions of the sky supports the theory of cosmic inflation, a period of rapid exponential expansion that occurred within the first fractions of a second after the Big Bang. Inflation smoothed out initial irregularities, resulting in the near-uniform backdrop observed today. One of the most significant aspects of the CMB is its utility in mapping the universe's large-scale structure. The angular power spectrum of CMB fluctuations reveals the size of the acoustic peaks, which correspond to sound waves propagating through the primordial plasma. These peaks encode information about the density, temperature, and velocity of matter and radiation in the early universe. By studying these features, cosmologists have been able to estimate critical parameters such as the Hubble constant, the rate of cosmic expansion, the density of dark matter, and the curvature of space. The discovery and ongoing study of the CMB have also opened new avenues for understanding the early universe's physics. For instance, the polarization of the CMB, a subtle alignment of light waves caused by scattering during recombination, provides additional information about the universe's ionization history and the presence of primordial gravitational waves. The detection of these gravitational waves, if confirmed, would offer direct evidence for cosmic inflation and deepen our understanding of fundamental forces. Despite the wealth of knowledge gleaned from the CMB, mysteries remain. For example, the cold spot, an unusually large and cooler region in the CMB, continues to puzzle scientists. While some theories suggest it may be the result of a large cosmic void, others propose more exotic explanations, such as the imprints of a multiverse. Similarly, subtle asymmetries in the CMB's temperature distribution challenge the notion of perfect isotropy and may hint at unknown physics or processes in the early universe. The study of the CMB is a testament to humanity's ability to decode the cosmos using advanced technology and theoretical ingenuity. By examining the faint relic radiation left over from the Big Bang, scientists have pieced together a narrative that spans nearly 14 billion years, from the universe's fiery origins to its current state of expansion and complexity. The CMB not only provides a snapshot of the infant universe but also serves as a foundation for exploring profound questions about the nature of matter, energy, and the ultimate fate of the cosmos. As observational techniques continue to improve, future studies of the CMB promise to unveil even more about the universe's hidden secrets. Projects like the Simons Observatory and next-generation space telescopes are poised to refine measurements of the CMB's polarization and uncover signatures of primordial phenomena. These advancements will not only sharpen our understanding of the cosmos's earliest moments but also test fundamental theories of physics, potentially leading to groundbreaking discoveries about the nature of dark matter, dark energy, and the fabric of spacetime itself. The cosmic dark ages represent a profound and mysterious chapter in the universe's history, spanning the period from approximately 380,000 years to nearly 1 billion years after the Big Bang. This era began after the universe had cooled sufficiently for light to decouple from matter during the epoch of recombination, when protons and electrons combined to form neutral hydrogen atoms. With the decoupling of photons, the universe became transparent, but it was devoid of any light-emitting sources, marking a time of darkness in the vast expanse of space. During these dark ages, the universe was a mostly featureless, homogeneous expanse of cold hydrogen gas. There were no stars, galaxies, or quasars to illuminate the cosmos, and the dominant forces shaping this period were gravity, and the residual heat from the Big Bang. Gravity, acting on small density fluctuations imprinted during the era of cosmic inflation, began to draw gas into denser regions. These tiny irregularities, detected as temperature fluctuations in the cosmic microwave background, CMB, served as seeds for the formation of the first structures in the universe. The transition from darkness to light occurred with the emergence of the first stars, known as population 3 stars. These stars, theorized to have formed approximately 100 to 200 million years after the Big Bang, were unique in several respects. Unlike later generations of stars, population 3 stars formed from primordial gas consisting almost entirely of hydrogen and helium, with virtually no heavier elements, metals, present. This lack of metallicity made these stars vastly different from the stars we observe today, influencing their formation, lifespan, and behavior. Population 3 stars were extraordinarily massive, with estimates suggesting that many were between 100 and 300 times the mass of the Sun. Their immense mass caused them to burn through their nuclear fuel at an incredible rate, leading to short lifespans of only a few million years. Despite their brevity, these stars played a critical role in shaping the universe by producing the first significant sources of light and energy. Their intense radiation and powerful stellar winds disrupted the surrounding gas, initiating the process of reionization. Reionization was a transformative epoch in the universe's history, marking the end of the cosmic dark ages. During this period, the ultraviolet light emitted by population 3 stars began to ionize the surrounding neutral hydrogen, breaking it apart into protons and electrons. This ionization process created bubbles of ionized gas that expanded and eventually overlapped, reionizing the intergalactic medium, IgM, and restoring transparency to the universe. By approximately 1 billion years after the Big Bang, most of the universe had transitioned from a neutral to an ionized state. The significance of reionization cannot be overstated. It paved the way for the formation of the first galaxies and the large-scale structures that dominate the universe today. Reionization allowed photons to travel freely once again, enabling the growth of luminous objects and the observable universe as we know it. Without this critical process, the universe would have remained shrouded in darkness, and the development of complex structures would have been stifled. The sources of reionization were not limited to population 3 stars. As the process advanced, other light-emitting objects, including the first galaxies and quasars, contributed significantly to reionizing the universe. The early galaxies, forming in dense regions of the cosmic web, produced abundant ultraviolet light, further ionizing hydrogen in their vicinity. Meanwhile, quasars, powered by supermassive black holes, emitted intense radiation, ionizing gas over vast distances. Together, these sources completed the reionization process, transforming the universe into a luminous and dynamic environment. Studying the cosmic dark ages and reionization presents significant challenges due to the immense distances and faint signals involved. However, advances in observational technology have allowed astronomers to probe this epoch in remarkable detail. Instruments like the James Webb Space Telescope, JWST, are designed to observe the first galaxies and stars, shedding light on the transition from darkness to light. The 21-centimeter hydrogen line, a faint radio signal emitted by neutral hydrogen, is another powerful tool for studying the cosmic dark ages, providing a direct probe of the universe before ionization. One of the most intriguing aspects of the cosmic dark ages is their role in setting the initial conditions for the universe's evolution. The density fluctuations that grew under gravity during this period laid the groundwork for the cosmic web, a vast network of interconnected filaments, clusters, and voids that structure the universe. These fluctuations, amplified by gravitational collapse, influenced the distribution of galaxies and other large-scale structures that we observe today. The Dark Ages also hold profound implications for the study of cosmology and fundamental physics. This era provides a unique laboratory for testing theories of structure formation, dark matter, and the physics of the early universe. For instance, the growth of density fluctuations during the Dark Ages is strongly influenced by the properties of dark matter, making this period crucial for understanding its nature. Additionally, the formation and evolution of population 3 stars offer insights into the processes that produced the universe's first heavy elements, which were essential for the development of planets and life. Despite the progress made in understanding the cosmic Dark Ages and reionization, many mysteries remain. The exact characteristics of population 3 stars, including their mass distribution, formation mechanisms, and contributions to reionization, are still not fully understood. Similarly, the timing and duration of reionization, as well as the relative contributions of different sources, continue to be active areas of research. Observations from future telescopes, such as the Square Kilometre Array, SKA, and next-generation ground-based observatories, are expected to provide new insights into these questions. The cosmic Dark Ages and reionization also have broader philosophical implications, highlighting the universe's journey from simplicity to complexity. The transition from a dark, featureless cosmos to one filled with light and structure mirrors the broader narrative of cosmic evolution, culminating in the emergence of stars, galaxies, and, ultimately, life. This transformation underscores the intricate interplay between physical processes and cosmic history, revealing the interconnectedness of phenomena across vast scales of time and space. The formation of stars is a cornerstone of cosmic evolution, driving the creation of the elements, illuminating the universe, and shaping its structure. Stars are born within vast, dense regions of gas and dust known as molecular clouds, also referred to as stellar nurseries. These clouds, composed primarily of hydrogen and helium, provide the raw material for star formation. The process begins with gravitational collapse, as regions within these clouds experience localized instabilities, causing them to condense into smaller, denser cores. This is the initial step in a transformative journey, culminating in the ignition of nuclear fusion, which marks the birth of a star. Within a molecular cloud, external factors such as shockwaves from nearby supernovae, collisions between gas clouds, or gravitational interactions can trigger the collapse of a dense core. As the gas and dust collapse under their own gravity, they form a rotating protostar, surrounded by a disk of material. This disk often serves as the reservoir for planetary formation in later stages. As the protostar contracts, the gravitational energy is converted into heat, raising its internal temperature and pressure. Once the core temperature reaches approximately 10 million Kelvin, hydrogen nuclei begin to fuse into helium in a process called nuclear fusion. This fusion releases an immense amount of energy, counteracting gravitational collapse and stabilizing the nascent star. The mass of a protostar plays a pivotal role in determining its subsequent evolution and characteristics. Massive stars, typically more than 8 times the mass of the Sun, have incredibly high core temperatures and pressures. These stars burn through their nuclear fuel rapidly, with lifespans measured in millions of years. Despite their short lives, massive stars play a disproportionately large role in enriching the universe. At the end of their lifespans, they undergo spectacular deaths as supernovae, ejecting their outer layers into space and leaving behind remnants, such as neutron stars or black holes. Conversely, low-mass stars, like our Sun, have much longer lifespans, often spanning billions of years. These stars burn their nuclear fuel more slowly and evolve gradually, transitioning through various stages such as the red giant phase before shedding their outer layers to form planetary nebulae. The remaining core becomes a white dwarf, which slowly cools over time. While less dramatic than supernovae, low-mass stars contribute significantly to the universe's enrichment, dispersing elements into the surrounding space. One of the most remarkable aspects of star formation is the production of heavier elements, a process called nucleosynthesis. Stars serve as cosmic forges, synthesizing elements such as carbon, oxygen, and iron through fusion. These elements are ejected into space during the later stages of a star's life, particularly during supernova explosions. The material expelled by dying stars enriches the interstellar medium, providing the building blocks for the next generation of stars, planets, and ultimately, life itself. This cycle of star birth, death, and renewal is fundamental to the universe's chemical evolution. The efficiency and rate of star formation vary across environments and epochs. In dense molecular clouds, regions with higher densities and pressures form stars more efficiently. These regions often contain clusters of stars, ranging from a few dozen to thousands, as gravitational forces draw material into multiple dense cores. Star formation rates are influenced by factors such as gas density, temperature, and the presence of magnetic fields or turbulence. Galactic environments also play a crucial role. Spiral galaxies like the Milky Way have active star-forming regions in their arms, while elliptical galaxies exhibit low rates due to their lack of cold gas. In the early universe, the first generation of stars, known as population 3 stars, formed from pristine clouds of hydrogen and helium left over from the Big Bang. These stars were likely massive, short-lived, and entirely devoid of heavier elements. Their deaths seeded the interstellar medium with the first traces of metals, paving the way for later generations of stars to form from enriched material. This progression highlights the interconnectedness of stellar evolution, and the chemical enrichment of the universe. Observational advancements have allowed astronomers to study star formation in unprecedented detail. Telescopes like the James Webb Space Telescope, JWST, and ALMA, Atacama Large Millimeter/Submillimeter Array, have provided insights into the processes occurring within molecular clouds. These instruments can detect the faint glow of protostars, map the distribution of gas and dust, and reveal the dynamics of star-forming regions. By studying these environments, scientists gain a deeper understanding of the conditions that lead to star formation and the factors influencing the diversity of stellar populations. Star formation is also intimately linked to galactic evolution. The energy output from stars, including radiation, stellar winds, and supernova explosions, significantly affects their surroundings. This feedback can compress nearby gas, triggering new star formation, or expel material from the region, inhibiting further star birth. This interplay between stars and their environments drives the formation and evolution of galaxies over cosmic timescales, shaping the large-scale structure of the universe. In addition to their role in galactic evolution, stars profoundly influence the habitability of planetary systems. Stars provide the energy necessary for maintaining conditions suitable for life, particularly on planets within the habitable zone, where liquid water can exist. The stability and lifespan of a star are critical factors in determining the potential for life to emerge and evolve. The Sun, a relatively stable and long-lived star, has provided a hospitable environment for life on Earth for nearly 4.5 billion years. The study of star formation continues to uncover new complexities and surprises. For example, recent observations have revealed the presence of massive stars in unexpected regions, challenging traditional models of stellar formation. Similarly, the discovery of stars with unusual chemical compositions provides clues about the processes occurring in the early universe. These findings highlight the dynamic and evolving nature of stellar astrophysics, underscoring the importance of ongoing exploration and research. The formation of stars is a transformative process that drives the universe's evolution, illuminates its vast expanse, and enriches its chemical composition. From the gravitational collapse of molecular clouds to the ignition of nuclear fusion, stars represent the pinnacle of cosmic creativity. Their diversity, influenced by mass, environment, and time, ensures a continuous cycle of birth, death, and renewal. As the engines of chemical enrichment, and the architects of galaxies, stars play an indispensable role in shaping the cosmos and fostering the conditions necessary for life. The ongoing study of star formation not only deepens our understanding of the universe but also connects us to its awe-inspiring processes that span billions of years. The formation of galaxies marks a defining moment in the cosmic narrative, representing the aggregation of matter into vast structures that host stars, planetary systems, and dark matter. Galaxies are the fundamental building blocks of the universe, and their formation is a complex interplay of gravitational forces, environmental conditions, and the mysterious influence of dark matter. This process began relatively early in cosmic history, within the first few 100 million years after the Big Bang, as density fluctuations in the primordial universe set the stage for matter to coalesce into the first galaxies. Galactic formation is deeply rooted in the gravitational collapse of gas clouds, where regions of higher density, seeded by quantum fluctuations during cosmic inflation, began pulling in surrounding material. This collapse was not a simple aggregation of baryonic, ordinary, matter but was heavily influenced by the presence of dark matter, a substance that does not emit, absorb, or reflect light but exerts a gravitational pull. The dark matter formed halos around regions of baryonic matter, creating a framework within which galaxies could assemble. These halos acted as gravitational wells, guiding gas and dust to their centers and initiating the galaxy formation process. As gas collapsed into these dark matter halos, it cooled and fragmented, creating the conditions necessary for star formation. The first stars in these proto-galaxies ignited, flooding their surroundings with light and heat. The intense radiation and stellar winds from these stars helped shape the surrounding environment, influencing the rate of star formation, and the distribution of gas. Over time, these nascent galaxies evolved through a combination of internal processes and external interactions, taking on diverse forms and structures. Galaxies are not isolated entities, they interact with their surroundings and with each other, shaping their evolution in significant ways. One of the most critical aspects of galactic evolution is collisions and mergers. When two galaxies come into close proximity, their mutual gravitational forces can distort their shapes, trigger bursts of star formation, and redistribute matter. These interactions often result in dramatic transformations, such as the merging of two spiral galaxies to form an elliptical galaxy or the creation of tidal tails and streams of stars extending from the main body of the galaxy. Mergers play a pivotal role in shaping the morphology and structure of galaxies. For example, spiral galaxies, like our Milky Way, have disk-like structures with defined spiral arms that are sites of active star formation. These galaxies are typically found in lower density environments, where interactions are less frequent, allowing them to retain their ordered shapes. On the other hand, elliptical galaxies are often the remnants of multiple mergers, with chaotic and spheroidal shapes that lack the distinctive features of spirals. They are found in dense regions like galaxy clusters, where interactions are more common. Irregular galaxies, as the name suggests, have no well-defined structure and are often the result of gravitational interactions or the disruptive effects of nearby galaxies. Environmental factors play a crucial role in determining the fate of galaxies. For instance, galaxies located in clusters experience a phenomenon known as ram pressure stripping, where the gas within a galaxy is stripped away by the intra-cluster medium as it moves through the cluster. This process can quench star formation by removing the raw material needed for new stars. Conversely, galaxies in more isolated regions retain their gas for longer periods, allowing star formation to continue unabated. The star formation rate within a galaxy is another key factor that influences its evolution. Galaxies with high star formation rates, known as starburst galaxies, are characterized by intense periods of star formation, often triggered by interactions or inflows of gas. These bursts can exhaust the galaxy's gas supply quickly, leading to a subsequent decline in star formation activity. In contrast, galaxies with lower star formation rates evolve more gradually, maintaining steady growth over billions of years. The role of dark matter in galaxy formation cannot be overstated. Observations of galaxy rotation curves have shown that the visible matter within galaxies is insufficient to account for their observed motions. This discrepancy is attributed to dark matter, which forms an invisible halo around galaxies, extending far beyond their visible boundaries. The gravitational influence of dark matter stabilizes galaxies, preventing them from dispersing and guiding their overall structure and dynamics. Without the presence of dark matter, it is unlikely that galaxies as we observe them today could have formed. One of the most intriguing aspects of galaxy formation is the hierarchical nature of the process. Small galaxies form first, merging over time to create larger and more complex structures. This bottom-up model, supported by observational evidence, suggests that the universe's largest galaxies, such as giant ellipticals, are the result of successive mergers of smaller galaxies. This hierarchical assembly is consistent with the predictions of cold dark matter models, which describe how dark matter clumps together and drives the formation of cosmic structures. Modern telescopes and observational tools have provided unprecedented insights into the galaxy formation process. The Hubble Space Telescope and the James Webb Space Telescope, JWST, have allowed astronomers to observe galaxies from different epochs, tracing their evolution over billions of years. By studying galaxies at various stages of development, researchers can reconstruct the history of galaxy formation and understand the factors that drive their diversity. Galaxies are not only fascinating objects in their own right but also play a critical role in the broader context of cosmic evolution. They serve as the environments where stars form, evolve, and die, enriching the universe with heavier elements through processes like supernovae and stellar winds. These elements, essential for the formation of planets and life, are distributed throughout the interstellar medium, contributing to the chemical evolution of the universe. The presence of supermassive black holes at the centers of most galaxies adds another layer of complexity to galaxy formation. These black holes, with masses ranging from millions to billions of times that of the Sun, influence their host galaxies through a process known as feedback. The energy released by material falling into a supermassive black hole can heat the surrounding gas, regulating star formation and shaping the galaxy's structure. This interplay between galaxies and their central black holes is a key area of research in modern astrophysics. The diversity of galaxy types and structures is a testament to the complex interplay of factors that govern their formation and evolution. From the elegant spirals of the Milky Way to the chaotic shapes of irregular galaxies, each galaxy tells a unique story of its origins and development. Understanding these processes not only deepens our knowledge of the universe but also provides insights into the conditions that made our own existence possible. Dark matter, an enigmatic and invisible form of matter, constitutes approximately 85% of the total matter in the universe, profoundly shaping its structure and evolution. Despite being undetectable through electromagnetic radiation, dark matter's presence is inferred from its gravitational effects, which are essential for understanding the behavior and distribution of galaxies, galaxy clusters, and cosmic large-scale structures. Its pervasive influence has made it a cornerstone of modern cosmology, even as its exact nature remains one of the most significant unsolved mysteries in physics. The concept of dark matter originated in the early 20th century, when astronomers began to notice discrepancies between the visible mass of galaxies and their observed gravitational behavior. In the 1930s, Fritz Zwicky provided some of the first compelling evidence for dark matter while studying galaxy clusters. He observed that the galaxies within the Coma cluster were moving at velocities too high to be explained by the visible mass alone. Zwicky proposed the existence of unseen matter, which he called Dunkelmaterie, dark matter, to account for this anomaly. This idea gained further support in the 1970s, when Vera Rubin and Kent Ford measured the rotational curves of spiral galaxies. They found that the outer regions of galaxies rotated at nearly constant speeds, defying expectations based on the visible distribution of stars and gas. The missing mass required to explain these observations became attributed to dark matter. The influence of dark matter extends far beyond individual galaxies. It is thought to form halos, vast, spherical regions of invisible matter surrounding galaxies. These halos act as gravitational anchors, preventing galaxies from flying apart as they rotate and stabilizing their overall structure. Without the presence of dark matter halos, the observed motions of stars and gas within galaxies would be impossible to explain. Additionally, dark matter plays a critical role in the formation of galaxies themselves. During the early stages of the universe, dark matter clumped together under the influence of gravity, creating the seeds for the formation of baryonic matter, ordinary matter. The gravitational wells created by these dark matter clumps provided the framework within which gas could collapse and form stars and galaxies. On a larger scale, dark matter governs the cosmic web, the vast network of filaments, clusters, and voids that make up the universe's large-scale structure. The distribution of dark matter determines where galaxies and galaxy clusters form, guiding the overall layout of the cosmos. Observational evidence for this cosmic web comes from techniques such as gravitational lensing, where the bending of light by massive dark matter structures reveals their presence. By mapping these distortions, astronomers can infer the distribution of dark matter and gain insights into its role in shaping the universe. Despite its profound influence, the true nature of dark matter remains elusive. It does not interact with light or other forms of electromagnetic radiation, making it undetectable through traditional telescopes. Instead, its presence is revealed only through gravitational interactions. This has led to extensive theoretical and experimental efforts to uncover the identity of dark matter. The leading candidates fall into two broad categories: WIMPs, weakly interacting massive particles, and axions. WIMPs are hypothetical particles that interact only through the weak nuclear force and gravity, making them challenging to detect. They are predicted by extensions of the standard model of particle physics, such as supersymmetry. Efforts to detect WIMPs include experiments using underground detectors, such as LUX-ZEPPELIN and XENONT, which search for rare interactions between WIMPs and ordinary matter. Although no direct detections have been made, these experiments have placed stringent limits on WIMP properties, guiding the search for dark matter. Axions, another leading candidate, are ultralight particles proposed as a solution to the strong CP problem in quantum chromodynamics. Unlike WIMPs, axions interact extremely weakly with all other particles, making them even more difficult to detect. Experiments such as the Axion Dark Matter Experiment, ADMX, aim to uncover axions by looking for their conversion into photons in the presence of a magnetic field. While the hunt for axions has yet to yield definitive results, ongoing research continues to refine our understanding of their potential properties. The study of dark matter also involves cosmological observations and simulations. For example, the cosmic microwave background, CMB, provides indirect evidence for dark matter. Tiny fluctuations in the CMB's temperature correspond to density variations in the early universe, influenced by the presence of dark matter. These variations seeded the formation of galaxies and the large-scale structure of the cosmos. By analyzing the CMB, scientists can estimate the relative proportions of dark matter, ordinary matter, and dark energy, confirming that dark matter constitutes approximately 25% of the universe's total energy density. Computer simulations, such as the Millennium Simulation and illustrious TNG, have been instrumental in understanding dark matter's role in structure formation. These simulations model the universe's evolution from the Big Bang to the present day, incorporating the effects of dark matter on galaxy formation and clustering. The results align closely with observational data, providing strong support for the existence of dark matter and its role in shaping the universe. While dark matter is central to our understanding of the cosmos, its existence raises profound questions about fundamental physics. If dark matter is composed of particles, their discovery would expand the Standard Model, shedding light on previously unexplored realms of particle physics. Alternatively, if dark matter arises from modifications to our understanding of gravity, such as in modified Newtonian dynamics, MOND, or scalar tensor theories, it would revolutionize our understanding of one of the universe's fundamental forces. The role of dark matter is not limited to its gravitational effects, it also has potential implications for galactic evolution and the emergence of life. The stability provided by dark matter halos ensures the longevity of galaxies, creating environments where stars can form, evolve, and die over billions of years. This stability is crucial for the development of planetary systems and the conditions necessary for life. Without dark matter, the universe's structure would be vastly different, potentially precluding the emergence of habitable worlds. In addition to its scientific importance, the search for dark matter exemplifies the interplay between theory and observation in advancing knowledge. From Zwickie's initial observations to cutting-edge particle detectors and telescopes, the quest to understand dark matter has pushed the boundaries of technology and inspired international collaboration. Facilities like the Large Hadron Collider, LHC, and future projects such as the Einstein Telescope continue to explore the frontier of physics, seeking to unravel the nature of this elusive substance. The Milky Way galaxy, our home in the universe, is an intricate and awe-inspiring structure, offering insights into the broader processes that govern galaxy formation and evolution. As a barred spiral galaxy, the Milky Way exemplifies the dynamism and complexity inherent in such systems, with its formation, structure, and ongoing interactions painting a vivid picture of cosmic history. Estimated to have formed approximately 13.6 billion years ago, the Milky Way emerged from the hierarchical assembly of smaller protogalaxies and gas clouds, its structure shaped through a series of mergers and accretion events over billions of years. The Milky Way's defining features include a central bulge, a sprawling disk with spiral arms, and a diffuse halo of stars and dark matter. At the heart of the galaxy lies Sagittarius A, a supermassive black hole with a mass of about 4 million times that of the Sun, exerting a gravitational influence that stabilizes the galactic core. Surrounding the central bulge are the galaxy's distinctive spiral arms, regions teeming with star formation, gas, and dust, which are interspersed with older, cooler stars. The galaxy is further enveloped by a halo, a vast, spherical region containing ancient stars, globular clusters, and dark matter that extends far beyond the visible disk. The Milky Way's central bulge is a densely packed region of stars, predominantly older and cooler than those found in the spiral arms. This bulge is thought to have formed early in the galaxy's history, during the rapid assembly of protogalactic fragments. Observations suggest that the bulge is slightly elongated, forming a bar-like structure that channels gas and stars toward the center. This bar plays a crucial role in the dynamics of the galaxy, redistributing angular momentum and driving the inflow of material that sustains the supermassive black hole at its core. Encircling the bulge is the disk of the Milky Way, a flat, rotating region where the majority of the galaxy's stars, gas, and dust are concentrated. The disk spans approximately 100,000 light-years in diameter and is divided into two main components, the thin disk and the thick disk. The thin disk contains the majority of the galaxy's younger stars, as well as regions of active star formation fueled by dense molecular clouds. These regions are particularly prominent in the spiral arms, where shock waves compress gas, triggering the birth of new stars. The thick disk, by contrast, hosts older stars with higher velocities relative to the galactic plane, suggesting a more tumultuous formation history, possibly influenced by mergers and accretion events. The spiral arms are among the most visually striking features of the Milky Way, with their winding patterns traced by bright, young stars, clusters, and nebulae. These arms are not static structures but are instead density waves, regions of higher density that propagate through the disk, compressing gas and promoting star formation as they pass. The Sun is located in the Orion Arm, a minor spur situated between the larger Sagittarius and Perseus arms. The position of the Sun, about 27,000 light-years from the galactic center, places it within the habitable zone of the galaxy, where conditions are relatively stable and conducive to the development of life. Beyond the visible disk lies the Milky Way's halo, a vast and diffuse region that extends several 100,000 light-years from the galactic center. The halo is composed of ancient stars, many of which reside in globular clusters, spherical groups of stars bound by gravity. These stars are among the oldest in the galaxy, providing valuable clues about its early formation. The halo also contains a significant amount of dark matter, an enigmatic substance that exerts gravitational influence but does not emit, absorb, or reflect light. Dark matter is thought to account for the majority of the Milky Way's mass, playing a crucial role in its structure and dynamics. The formation of the Milky Way was a gradual process that unfolded over billions of years. In its earliest stages, the galaxy began as a collection of small protogalaxies and gas clouds, which coalesced under gravity to form larger structures. This hierarchical assembly was marked by intense star formation, as gas cooled and collapsed into dense regions. The oldest stars in the galaxy, found in the halo and globular clusters, are relics of this early epoch. As the Milky Way grew, it underwent a series of mergers with other galaxies, each event contributing to its mass and reshaping its structure. These interactions also likely triggered bursts of star formation, enriching the galaxy's interstellar medium with heavier elements produced by stellar nucleosynthesis. The evolution of the Milky Way has been shaped not only by internal processes but also by interactions with its environment. The galaxy is part of the Local Group, a collection of more than 50 galaxies, including the Andromeda Galaxy and the Triangulum Galaxy, bound together by gravity. The Milky Way's gravitational influence extends to its satellite galaxies, such as the Large and Small Magellanic Clouds. These interactions have a profound impact on the Milky Way's structure and evolution, as the accretion of material from satellite galaxies contributes to its growth, while tidal forces shape the orbits and morphology of the satellites. One of the most significant ongoing interactions is the eventual collision between the Milky Way and the Andromeda Galaxy, predicted to occur in about 4.5 billion years. This cosmic event will reshape both galaxies, likely resulting in the formation of a single, larger elliptical galaxy. Although such collisions are dramatic, the vast distances between stars mean that individual stellar collisions are rare. Instead, the gravitational forces will rearrange the stars, gas, and dark matter, creating new structures and triggering bursts of star formation. The Milky Way's interstellar medium, the gas and dust that fills the space between stars, is a dynamic and vital component of the galaxy. This medium acts as the reservoir for star formation, with dense molecular clouds serving as the cradles of new stars. The interstellar medium is enriched by the death of massive stars, which expel heavy elements into space through supernova explosions. These elements, such as carbon, oxygen, and iron, are critical for the formation of planets and life, highlighting the interconnectedness of cosmic processes. The exploration of the Milky Way has advanced significantly over the past century, driven by developments in observational technology and theoretical modeling. Telescopes operating across the electromagnetic spectrum, from radio waves to gamma rays, have provided detailed views of the galaxy's structure and composition. Surveys like the Sloan Digital Sky Survey, SDSS, and the Gaia mission have mapped the positions, motions, and properties of millions of stars, offering unprecedented insights into the galaxy's dynamics and history. The Gaia mission, in particular, has revolutionized our understanding of the Milky Way by producing a detailed three-dimensional map of its stars. This data has enabled astronomers to reconstruct the galaxy's formation history, identifying remnants of past mergers and mapping the distribution of dark matter. Gaia's observations have also revealed the presence of stellar streams, elongated groups of stars that are the remnants of disrupted satellite galaxies and globular clusters. These streams provide direct evidence of the Milky Way's hierarchical growth and offer a unique window into the galaxy's gravitational potential. The study of the Milky Way is not limited to its visible components. Observations of high-energy phenomena, such as gamma-ray bursts and X-ray emissions, have revealed the presence of exotic objects like neutron stars and black holes. These remnants of massive stars provide critical tests for theories of gravity and the behavior of matter under extreme conditions. The detection of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, has further expanded our ability to study the Milky Way's most energetic events. Despite these advancements, many mysteries about the Milky Way remain. The nature of dark matter, the processes governing star formation, and the detailed history of the galaxy's interactions with its environment are active areas of research. Future missions, such as the James Webb Space Telescope and next-generation radio observatories, promise to shed light on these questions, providing deeper insights into the galaxy's past, present, and future. The Milky Way galaxy is a microcosm of the universe, encapsulating the processes that shape galaxies on all scales. Its formation, structure, and evolution reflect the interplay of gravity, radiation, and cosmic chemistry, offering a window into the broader workings of the cosmos. As our understanding of the Milky Way deepens, so too does our appreciation for the interconnectedness of the universe and our place within it. From the ancient stars in the halo to the vibrant regions of star formation in the spiral arms, the Milky Way tells a story of transformation, resilience, and the enduring power of cosmic forces. The Milky Way's formation traces back to the early universe, emerging shortly after the Big Bang, about 13.8 billion years ago. In its infancy, the universe was a hot and dense expanse filled with hydrogen and helium, the building blocks of the first stars and galaxies. Small density fluctuations in this primordial medium provided the seeds for gravitational collapse, leading to the formation of the first proto-galaxies. These early structures, dominated by dark matter halos, began merging under the influence of gravity, giving rise to larger systems, including the Milky Way. Over the course of billions of years, these mergers and accretions built the Milky Way's current structure. Evidence of this hierarchical growth is preserved in the stellar halo, which contains ancient stars and remnants of smaller galaxies that were absorbed into the Milky Way. The galaxy's globular clusters, dense groups of old stars orbiting in the halo, are also relics of this early period, providing clues about the conditions that prevailed during the galaxy's formative stages. The central bulge of the Milky Way is a densely packed region of stars surrounding Sagittarius A. This bulge is shaped like a bar and rotates as a cohesive structure, influencing the movement of stars and gas within the inner galaxy. It contains a mix of older, metal-rich stars and younger populations, reflecting the complex history of star formation and dynamical interactions in this region. Extending from the central bulge are the galaxy's spiral arms, which form a grand, rotating disk structure. The Milky Way's disk is about 100,000 light-years in diameter and contains the majority of the galaxy's stars, gas, and dust. The spiral arms, such as the Orion Arm where the solar system resides, are regions of active star formation fueled by the compression of gas as it moves through the galaxy's density waves. These arms host vibrant stellar nurseries, producing young, massive stars that illuminate and shape their surroundings. Beyond the visible disk lies the Milky Way's halo, a sparse but expansive region populated by ancient stars, globular clusters, and the invisible influence of dark matter. The halo extends for hundreds of thousands of light years, encompassing the galaxy and stabilizing its rotation through the gravitational pull of its dark matter component. Observations of halo stars reveal the remnants of past mergers, with their orbits and compositions providing a fossil record of the galaxy's accretion history. At the very center of the Milky Way lies Sagittarius A, a supermassive black hole that exerts a profound influence on its surroundings. Observations of stellar motions near Sagittarius A have allowed astronomers to precisely estimate its mass, confirming its status as one of the densest objects in the galaxy. Although Sagittarius A is relatively quiet compared to the active black holes in quasars, it occasionally flares, emitting bursts of radiation as it accretes material. The presence of this black hole is a key factor in shaping the dynamics of the galactic core and influencing star formation in its vicinity. Sagittarius A resides in the galactic center, a region densely packed with stars, gas and dust. This area is one of the most studied parts of the Milky Way, as it provides a unique opportunity to observe the effects of a supermassive black hole on its immediate environment. Sagittarius A has an estimated mass of about 4 million times that of the Sun. Despite its immense mass, it occupies a surprisingly small volume, making it one of the densest known objects. This extreme density is a defining characteristic of black holes, where gravity is so intense that nothing, not even light, can escape. Astronomers have employed various techniques to study Sagittarius A. One of the most significant breakthroughs came from observing the motions of stars orbiting the black hole. By tracking these stellar orbits over decades, scientists have been able to calculate the mass of Sagittarius A with remarkable precision. These observations have also provided compelling evidence for the existence of black holes, as no other known object could account for the observed gravitational effects. The environment around Sagittarius A is dynamic and complex. The galactic center hosts a diverse array of phenomena, including high-energy radiation, strong magnetic fields, and turbulent flows of gas and dust. These conditions create a challenging yet fascinating laboratory for studying astrophysical processes. Material in the vicinity of Sagittarius A is drawn toward the black hole, forming an accretion disk. As matter spirals inward, it heats up and emits radiation, particularly in the X-ray and infrared wavelengths. While Sagittarius A is not classified as an active galactic nucleus, AGN, it occasionally experiences flares, during which it emits bursts of energy. These flares are thought to result from sudden increases in the accretion rate, such as when a clump of gas or a small object falls into the black hole. The relative quietness of Sagittarius A compared to active black holes in quasars can be attributed to its low accretion rate. In quasars, supermassive black holes consume vast amounts of material, producing intense radiation and powerful jets. In contrast, Sagittarius A accretes material at a much slower pace, leading to lower luminosity. However, this does not diminish its importance. Even in its subdued state, Sagittarius A exerts a profound influence on the galactic center. One of the most intriguing aspects of Sagittarius A is its role in shaping the dynamics of the surrounding region. The immense gravitational pull of the black hole dominates the central few light-years of the galaxy, affecting the orbits of stars and gas clouds. This influence extends to star formation, as the gravitational forces and energetic processes near Sagittarius A can compress gas clouds, triggering the birth of new stars. Conversely, the same forces can also disrupt star-forming regions, highlighting the complex interplay between the black hole and its environment. The study of Sagittarius A has also shed light on the broader context of galaxy evolution. Supermassive black holes are thought to reside at the centers of most, if not all, galaxies. These black holes and their host galaxies are believed to co-evolve, influencing each other's growth and development. By studying Sagittarius A, astronomers can gain insights into these processes and better understand the connections between black holes and galaxies. Advancements in observational technology have been instrumental in unraveling the mysteries of Sagittarius A. Instruments like the Very Large Telescope, VLT, and the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided high-resolution images and spectra of the galactic center. The Event Horizon Telescope, EHT, collaboration achieved a landmark accomplishment by capturing the first image of a black hole's shadow, demonstrating the feasibility of directly imaging these enigmatic objects. Efforts are underway to apply similar techniques to Sagittarius A, which could yield groundbreaking results. The exploration of Sagittarius A has also been a driving force behind theoretical developments in astrophysics. Models of black hole accretion, jet formation, and relativistic effects have been tested and refined using data from the galactic center. For example, the extreme gravitational field near Sagittarius A provides an ideal setting to test Einstein's general theory of relativity. Observations of stellar orbits and light bending near the black hole have confirmed the theory's predictions to an unprecedented degree of accuracy. Despite the progress made, many questions about Sagittarius A remain unanswered. The exact mechanisms governing its flares, the properties of its accretion disk, and its long-term impact on the galactic center are active areas of research. Additionally, the role of magnetic fields and their interactions with the black hole's surroundings is not fully understood. These mysteries continue to inspire astronomers and physicists, driving efforts to develop more sophisticated models and conduct more detailed observations. The study of Sagittarius A has implications that extend beyond the Milky Way. Understanding the behavior of supermassive black holes in general can provide insights into the nature of gravity, the behavior of matter under extreme conditions, and the formation and evolution of cosmic structures. Sagittarius A, as the closest supermassive black hole to Earth, serves as a natural laboratory for exploring these fundamental questions. The Milky Way does not exist in isolation. It interacts with a host of satellite galaxies, the most prominent being the Magellanic Clouds, the Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC. These dwarf galaxies, visible from the southern hemisphere, are gravitationally bound to the Milky Way and are in the process of being accreted into its structure. Their interactions with the Milky Way generate tidal streams of gas and stars, such as the Magellanic Stream, which stretches across the sky and fuels star formation in the Milky Way's outer regions. The Sagittarius dwarf galaxy is another notable satellite, currently being torn apart as it orbits the Milky Way. Its stellar debris forms the Sagittarius Stream, a looping structure that wraps around the galaxy and provides direct evidence of ongoing accretion. These interactions highlight the dynamic nature of the Milky Way, as it continues to grow and evolve through the assimilation of smaller systems. The Milky Way is a site of prolific star formation, particularly within its spiral arms. These regions are dynamic and bustling with activity, where the interplay of gravity, gas dynamics, and stellar feedback orchestrates the birth of stars. Stellar nurseries like the Orion Nebula and the Carina Nebula exemplify the vibrant processes that define star formation. Within these nurseries, clouds of gas and dust collapse under the influence of gravity, initiating the formation of protostars. As these protostars gather mass and heat up, they eventually ignite nuclear fusion, marking their transformation into main sequence stars. This process not only fuels the galaxy's brightness but also drives its ongoing evolution. Star formation in the Milky Way is concentrated in its spiral arms, which serve as reservoirs of dense molecular gas. These arms are density waves, regions of higher density that sweep through the galactic disk, compressing gas and triggering star formation. This phenomenon creates a pattern of bright, young stars and star clusters tracing the spiral structure of the galaxy. The Sun itself resides in the Orion Arm, a minor spur between the larger Sagittarius and Perseus arms. This location places our solar system within an area of moderate star formation activity, shielded from the more intense processes occurring closer to the galactic center. Regions like the Orion Nebula are iconic examples of stellar nurseries. Located about 1,344 light-years away, the Orion Nebula is part of a larger molecular cloud complex and hosts a rich population of young stars. Observations of this region reveal a dynamic environment where protostars and newly formed stars interact with their surroundings. Stellar winds, radiation, and outflows from these young stars shape the surrounding gas and dust, creating intricate structures and influencing the next generation of star formation. The Carina Nebula, another prominent stellar nursery, lies approximately 8,500 light-years away in the Carina Sagittarius Arm. It is home to some of the most massive and luminous stars known, including Eta Carini, a binary system on the brink of a dramatic supernova. Massive stars like those in the Carina Nebula play a dual role in star formation. On one hand, their intense radiation and stellar winds can compress nearby gas, triggering the collapse of molecular clouds and the formation of new stars. On the other hand, these same forces can disrupt star-forming regions, dispersing gas and halting further star formation. The balance between star formation and the consumption of gas in the Milky Way is influenced by a variety of feedback mechanisms. Supernovae, the explosive deaths of massive stars, are among the most impactful feedback processes. When a star explodes as a supernova, it releases an enormous amount of energy into its surroundings, heating and dispersing gas. This process can inhibit star formation by depleting the dense gas required for new stars. However, supernovae also play a constructive role by enriching the interstellar medium with heavy elements, such as carbon, oxygen, and iron. These elements are the building blocks of planets and life, underscoring the importance of supernovae in the chemical evolution of the galaxy. Stellar winds from massive stars also contribute to feedback in star-forming regions. These winds are streams of charged particles that are ejected from the surfaces of stars at high velocities. Like supernovae, stellar winds can both hinder and promote star formation. By clearing out gas and dust, stellar winds create cavities in molecular clouds, shaping the structure of star-forming regions. Simultaneously, the compression of gas at the edges of these cavities can lead to the formation of new stars, continuing the cycle of stellar birth and feedback. Interactions with satellite galaxies further influence star formation in the Milky Way. The gravitational pull of nearby galaxies, such as the Large and Small Magellanic Clouds, distorts the Milky Way's disk and induces flows of gas. These interactions can funnel gas into the galaxy, replenishing its star-forming reservoirs and triggering bursts of star formation. The Magellanic Stream, a stream of gas stretching between the Milky Way and its satellite galaxies, exemplifies this process. This influx of material sustains the galaxy's star formation rate and contributes to its long-term evolution. The interstellar medium, ISM, of the Milky Way is a critical component of its star formation processes. The ISM consists of gas and dust that fills the space between stars, serving as the raw material for new stars. It is composed of various phases, including cold molecular clouds, warm ionized gas, and hot diffuse plasma. Molecular clouds are the densest regions of the ISM, and are the primary sites of star formation. These clouds are rich in molecular hydrogen, H2, and are often traced by the emission of carbon monoxide, CO, a molecule that is more easily detectable. The collapse of molecular clouds into stars is governed by a delicate balance of forces. Gravity acts to pull the gas inward, while thermal pressure, magnetic fields, and turbulence counteract this collapse. When the density of a cloud reaches a critical threshold, Gravity overcomes these opposing forces, leading to the formation of dense cores. These cores continue to collapse, forming protostars that accrete mass from their surroundings. Over time, the protostars heat up, and once nuclear fusion begins, they become main sequence stars. The efficiency of star formation varies across the Milky Way, with some regions being more prolific than others. Factors such as the availability of gas, the presence of density waves in spiral arms, and the influence of feedback processes determine the rate of star formation. The Milky Way's star formation rate is estimated to be about 1 to 2 solar masses per year, indicating a steady but not overly rapid pace of stellar production. This rate reflects a balance between the consumption of gas through star formation and its replenishment through processes like accretion and mergers. The chemical evolution of the Milky Way is closely tied to its star formation history. As stars age and die, they release heavy elements into the ISM through stellar winds, supernovae, and the shedding of outer layers by red giants. These elements, collectively referred to as metals in astronomical terms, enrich the ISM and are incorporated into subsequent generations of stars and planets. The presence of heavier elements is a key factor in the formation of rocky planets and the potential for life. Observations of the Milky Way's metallicity gradient, the variation in metal content with distance from the galactic center, provide insights into the processes that have shaped the galaxy's chemical composition over time. Star clusters offer a window into the star formation processes of the Milky Way. These clusters are groups of stars that form together from the same molecular cloud and are bound by gravity. Open clusters, which are loosely bound and contain younger stars, are often found in the spiral arms. In contrast, globular clusters are tightly bound and contain older stars, typically residing in the halo of the galaxy. The study of star clusters reveals information about the initial conditions of star formation, the life cycles of stars, and the dynamical evolution of the galaxy. Technological advancements have significantly enhanced our understanding of star formation in the Milky Way. Observatories operating across the electromagnetic spectrum have provided detailed views of star-forming regions and the ISM. For example, radio telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, have enabled the observation of molecular clouds in unprecedented detail, while infrared observatories like the Spitzer Space Telescope have penetrated the dusty regions where stars are born. High-resolution imaging and spectroscopy have revealed the intricate interplay of gas, dust, and stars in star-forming regions, offering a deeper understanding of the underlying physics. Theoretical models and simulations complement observational studies, providing insights into the complex processes driving star formation. These models incorporate the effects of gravity, turbulence, magnetic fields, and feedback mechanisms to simulate the evolution of molecular clouds and the formation of stars. Advances in computational power have allowed for increasingly sophisticated simulations, enabling researchers to explore the conditions under which stars form and the factors that influence their properties. Despite significant progress, many questions about star formation in the Milky Way remain unanswered. The precise mechanisms that regulate the efficiency of star formation, the role of magnetic fields, and the interplay between feedback processes and the ISM are active areas of research. Future missions, such as the James Webb Space Telescope and next-generation radio observatories, promise to address these questions, offering new insights into the fundamental processes that shape our galaxy. The cycle of star formation and feedback is a defining characteristic of the Milky Way, driving its evolution and enriching its interstellar medium with the elements necessary for planets and life. This cycle underscores the interconnectedness of cosmic processes, from the collapse of molecular clouds to the explosive deaths of stars. As we continue to explore the Milky Way, both through observations and theoretical models, we deepen our understanding of the galaxy's intricate workings and its place in the broader universe. The Milky Way's stability and rotation are governed by the presence of an extensive dark matter halo, which outweighs the visible mass of the galaxy by a significant margin. This halo provides the gravitational pull necessary to hold the galaxy together, particularly at its outer edges, where the observed rotation curves deviate from expectations based solely on visible matter. The dark matter halo not only stabilizes the Milky Way, but also influences its interactions with neighboring galaxies, shaping the larger-scale structure of the local group. The Milky Way is a site of prolific star formation, particularly within its spiral arms. These regions are dynamic and bustling with activity, where the interplay of gravity, gas dynamics, and stellar feedback orchestrates the birth of stars. Stellar nurseries like the Orion Nebula and the Carina Nebula exemplify the vibrant processes that define star formation. Within these nurseries, clouds of gas and dust collapse under the influence of gravity, initiating the formation of protostars. As these protostars gather mass and heat up, they eventually ignite nuclear fusion, marking their transformation into main sequence stars. This process not only fuels the galaxy's brightness but also drives its ongoing evolution. Star formation in the Milky Way is concentrated in its spiral arms, which serve as reservoirs of dense molecular gas. These arms are density waves, regions of higher density that sweep through the galactic disk, compressing gas and triggering star formation. This phenomenon creates a pattern of bright, young stars and star clusters tracing the spiral structure of the galaxy. The Sun itself resides in the Orion Arm, a minor spur between the larger Sagittarius and Perseus arms. This location places our solar system within an area of moderate star formation activity, shielded from the more intense processes occurring closer to the galactic center. Regions like the Orion Nebula are iconic examples of stellar nurseries. Located about 1,344 light-years away, the Orion Nebula is part of a larger molecular cloud complex and hosts a rich population of young stars. Observations of this region reveal a dynamic environment where protostars and newly formed stars interact with their surroundings. Stellar winds, radiation, and outflows from these young stars shape the surrounding gas and dust, creating intricate structures and influencing the next generation of star formation. The Carina Nebula, another prominent stellar nursery, lies approximately 8,500 light-years away in the Carina Sagittarius Arm. It is home to some of the most massive and luminous stars known, including Eta Carini, a binary system on the brink of a dramatic supernova. Massive stars like those in the Carina Nebula play a dual role in star formation. On one hand, their intense radiation and stellar winds can compress nearby gas, triggering the collapse of molecular clouds and the formation of new stars. On the other hand, these same forces can disrupt star-forming regions, dispersing gas and halting further star formation. The balance between star formation and the consumption of gas in the Milky Way is influenced by a variety of feedback mechanisms. Supernovae, the explosive deaths of massive stars, are among the most impactful feedback processes. When a star explodes as a supernova, it releases an enormous amount of energy into its surroundings, heating and dispersing gas. This process can inhibit star formation by depleting the dense gas required for new stars. However, supernovae also play a constructive role by enriching the interstellar medium with heavy elements, such as carbon, oxygen, and iron. These elements are the building blocks of planets and life, underscoring the importance of supernovae in the chemical evolution of the galaxy. Stellar winds from massive stars also contribute to feedback in star-forming regions. These winds are streams of charged particles that are ejected from the surfaces of stars at high velocities. Like supernovae, stellar winds can both hinder and promote star formation. By clearing out gas and dust, stellar winds create cavities in molecular clouds, shaping the structure of star-forming regions. Simultaneously, the compression of gas at the edges of these cavities can lead to the formation of new stars, continuing the cycle of stellar birth and feedback. Interactions with satellite galaxies further influence star formation in the Milky Way. The gravitational pull of nearby galaxies, such as the Large and Small Magellanic Clouds, distorts the Milky Way's disk and induces flows of gas. These interactions can funnel gas into the galaxy, replenishing its star-forming reservoirs and triggering bursts of star formation. The Magellanic Stream, a stream of gas stretching between the Milky Way and its satellite galaxies, exemplifies this process. This influx of material sustains the galaxy's star formation rate and contributes to its long-term evolution. The interstellar medium, ISM, of the Milky Way is a critical component of its star formation processes. The ISM consists of gas and dust that fills the space between stars, serving as the raw material for new stars. It is composed of various phases, including cold molecular clouds, warm ionized gas, and hot diffuse plasma. Molecular clouds are the densest regions of the ISM, and are the primary sites of star formation. These clouds are rich in molecular hydrogen, H2, and are often traced by the emission of carbon monoxide, CO, a molecule that is more easily detectable. The collapse of molecular clouds into stars is governed by a delicate balance of forces. Gravity acts to pull the gas inward, while thermal pressure, magnetic fields, and turbulence counteract this collapse. When the density of a cloud reaches a critical threshold, gravity overcomes these opposing forces, leading to the formation of dense cores. These cores continue to collapse, forming protostars that accrete mass from their surroundings. Over time, the protostars heat up, and once nuclear fusion begins, they become main sequence stars. The efficiency of star formation varies across the Milky Way, with some regions being more prolific than others. Factors such as the availability of gas, the presence of density waves in spiral arms, and the influence of feedback processes determine the rate of star formation. The Milky Way's star formation rate is estimated to be about 1 to 2 solar masses per year, indicating a steady but not overly rapid pace of stellar production. This rate reflects a balance between the consumption of gas through star formation and its replenishment through processes like accretion and mergers. The chemical evolution of the Milky Way is closely tied to its star formation history. As stars age and die, they release heavy elements into the ISM through stellar winds, supernovae, and the shedding of outer layers by red giants. These elements, collectively referred to as metals in astronomical terms, enrich the ISM and are incorporated into subsequent generations of stars and planets. The presence of heavier elements is a key factor in the formation of rocky planets and the potential for life. Observations of the Milky Way's metallicity gradient, the variation in metal content with distance from the galactic center, provide insights into the processes that have shaped the galaxy's chemical composition over time. Star clusters offer a window into the star formation processes of the Milky Way. These clusters are groups of stars that form together from the same molecular cloud and are bound by gravity. Open clusters, which are loosely bound and contain younger stars, are often found in the spiral arms. In contrast, globular clusters are tightly bound and contain older stars, typically residing in the halo of the galaxy. The study of star clusters reveals information about the initial conditions of star formation, the life cycles of stars, and the dynamical evolution of the galaxy. Technological advancements have significantly enhanced our understanding of star formation in the Milky Way. Observatories operating across the electromagnetic spectrum have provided detailed views of star-forming regions and the ISM. For example, radio telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, have enabled the observation of molecular clouds in unprecedented detail, while infrared observatories like the Spitzer Space Telescope have penetrated the dusty regions where stars are born. High-resolution imaging and spectroscopy have revealed the intricate interplay of gas, dust, and stars in star-forming regions, offering a deeper understanding of the underlying physics. Theoretical models and simulations complement observational studies, providing insights into the complex processes driving star formation. These models incorporate the effects of gravity, turbulence, magnetic fields, and feedback mechanisms to simulate the evolution of molecular clouds and the formation of stars. Advances in computational power have allowed for increasingly sophisticated simulations, enabling researchers to explore the conditions under which stars form and the factors that influence their properties. Despite significant progress, many questions about star formation in the Milky Way remain unanswered. The precise mechanisms that regulate the efficiency of star formation, the role of magnetic fields, and the interplay between feedback processes and the ISM are active areas of research. Future missions, such as the James Webb Space Telescope and next-generation radio observatories, promise to address these questions, offering new insights into the fundamental processes that shape our galaxy. The cycle of star formation and feedback is a defining characteristic of the Milky Way, driving its evolution and enriching its interstellar medium with the elements necessary for planets and life. This cycle underscores the interconnectedness of cosmic processes, from the collapse of molecular clouds to the explosive deaths of stars. As we continue to explore the Milky Way, both through observations and theoretical models, we deepen our understanding of the galaxy's intricate workings and its place in the broader universe. The Milky Way's evolution is far from complete. Over the next 4 billion years, it is expected to merge with the Andromeda Galaxy, the largest galaxy in the local group. This collision will result in a dramatic transformation, as the two galaxies merge to form a massive elliptical galaxy, sometimes referred to as Milkomeda. While the process will disrupt the Milky Way's current structure, it will also give rise to new bursts of star formation and reshape the distribution of stars and gas. The Milky Way is not only our cosmic home but also a microcosm of galactic processes that occur throughout the universe. Its structure, dynamics, and interactions reflect the universal principles of galaxy formation and evolution, providing a laboratory for understanding the cosmos. From the earliest proto-galaxies to the future merger with Andromeda, the Milky Way's journey is a testament to the intricate interplay of gravity, dark matter, and cosmic history. Approximately 4.6 billion years ago, the Solar System began its journey as a dense region within a molecular cloud nestled in the Milky Way galaxy. This cloud, composed primarily of hydrogen, helium, and trace amounts of heavier elements, likely became unstable due to a nearby supernova explosion or gravitational disturbances, triggering its collapse under gravity. As the cloud condensed, it formed a rotating protoplanetary disk, with most of the mass accumulating at the center to ignite the birth of the Sun, our star. This collapse marked the initial stage of a dynamic and intricate process that led to the formation of the Sun, planets, moons, asteroids, and comets, creating the complex system we inhabit today. At the center of the disk, temperatures and pressures increased dramatically, igniting nuclear fusion and giving birth to the Sun. Surrounding the young Sun, the remaining material in the disk began to coalesce through a process called accretion, where dust grains collided and stuck together, forming planetesimiles, small celestial bodies that served as the building blocks of planets. The temperature gradient within the disk played a crucial role in determining the types of planets that would form. In the hotter inner regions, only materials with high melting points, such as metals and silicates, could condense, leading to the formation of the terrestrial planets, Mercury, Venus, Earth, and Mars. Farther from the Sun, in the cooler outer regions, volatile compounds like water, ammonia, and methane could freeze, allowing for the development of gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. The formation of these planets was not a smooth or uniform process. The early solar system was a chaotic environment, with collisions between planetesimiles playing a pivotal role in shaping planetary bodies. These violent impacts not only influenced the size and composition of the planets but also generated immense heat, contributing to the differentiation of planetary interiors. For instance, Earth's dense iron core and silicate mantle formed, during this time, as heavier elements sank to the center while lighter materials rose to the surface. One of the most significant events in the Solar System's history was the Late Heavy Bombardment, LHB, a period of intense asteroid and comet impacts that occurred approximately 4.1 to 3.8 billion years ago. During this time, leftover planetesimiles from the formation process bombarded the inner planets, reshaping their surfaces and leaving behind craters that are still visible today, particularly on the Moon and Mercury. The LHB also played a critical role in Earth's evolution, potentially delivering water and organic compounds that contributed to the emergence of life. Earth's unique position within the habitable zone, the region around the Sun where temperatures allow liquid water to exist, was crucial for the development of life. Several factors combined to create the conditions necessary for life to thrive on Earth. The planet's stable orbit, moderate size, and distance from the Sun provided an environment where liquid water could persist on the surface. Additionally, the presence of a magnetic field, generated by Earth's molten iron core, protected the planet from harmful solar radiation, while the atmosphere, rich in carbon dioxide, nitrogen, and water vapor, helped regulate surface temperatures. The Moon, formed approximately 4.5 billion years ago from the debris of a massive collision between Earth and a Mars-sized body called Theia, also played a significant role in Earth's habitability. The Moon's gravitational pull stabilizes Earth's axial tilt, reducing climatic extremes and creating a more stable environment for life to evolve. Tidal forces generated by the Moon also influenced the early development of Earth's oceans, fostering conditions for the emergence of primitive life forms. As Earth cooled, water vapor in the atmosphere condensed to form the first oceans, and volcanic activity released gases that contributed to the development of the planet's early atmosphere. By around 3.8 billion years ago, conditions on Earth had stabilized enough to support the earliest forms of microbial life, marking the beginning of a biological legacy that would eventually lead to the complex ecosystems we see today. The interplay between Earth's geological activity and its developing biosphere continued to shape the planet over billions of years, creating a dynamic and evolving environment. The outer planets, though inhospitable to life as we know it, play crucial roles within the solar system. Jupiter, the largest planet, acts as a gravitational shield, deflecting or capturing many comets and asteroids that might otherwise impact the inner planets. Its immense gravity has influenced the orbits of other celestial bodies, shaping the architecture of the solar system. Meanwhile, the moons of the outer planets, such as Europa, Enceladus, and Titan, have become prime targets in the search for extraterrestrial life, as they are believed to harbor subsurface oceans or conditions that could support life. Asteroids and comets, the remnants of the early solar system, offer valuable insights into its formation and evolution. These small bodies, composed of primitive material, serve as time capsules, preserving the conditions and composition of the protoplanetary disk. Missions such as NASA's OSIRIS-REx and ESA's Rosetta have provided critical data about these objects, enhancing our understanding of the processes that shaped the solar system. The solar system continues to evolve, albeit on timescales far longer than human perception. The Sun, currently in its main sequence phase, will eventually exhaust its hydrogen fuel and transition into a red giant, engulfing the inner planets, including Earth. This transformation, expected to occur in approximately 5 billion years, will mark the end of the solar system as we know it. However, long before this cosmic finale, the ongoing study of our celestial neighborhood will provide deeper insights into its origins and the fundamental processes that govern planetary systems across the universe. The formation of the solar system is not just a tale of celestial mechanics and chemical processes, it is a story of transformation, resilience, and interconnectedness. From the initial collapse of a molecular cloud to the emergence of life on Earth, each step in this journey reflects the delicate balance of forces that have shaped our cosmic environment. As we continue to explore the solar system through telescopes, space probes, and theoretical models, we gain not only a better understanding of its past but also a glimpse into the broader workings of the universe. As the cloud collapsed, it began to spin faster due to the conservation of angular momentum. This rotation caused the material to flatten into a protoplanetary disk, with the majority of the mass concentrated at the center. This dense core eventually ignited nuclear fusion, giving birth to our Sun. The remaining material in the disk provided the raw ingredients for the formation of planets and other structures. Within this disk, a process known as accretion began to shape the future of the solar system. Accretion refers to the gradual growth of larger bodies from smaller particles. Dust grains within the disk collided and stuck together, forming pebbles, then larger rocks, and eventually planetesimals, the building blocks of planets. Over time, these planetesimals coalesced into protoplanets through gravitational attraction. The early solar system was a chaotic environment, with frequent collisions and interactions shaping the trajectories and compositions of forming bodies. The inner regions of the protoplanetary disk, closer to the Sun, were dominated by rocky materials that could withstand the intense heat. Here, the terrestrial planets, Mercury, Venus, Earth, and Mars, formed. In contrast, the cooler outer regions allowed for the accumulation of volatile compounds like water, methane, and ammonia, enabling the formation of gas giants like Jupiter and Saturn, and ice giants like Uranus and Neptune. These planets, with their substantial gravitational influence, played a crucial role in shaping the architecture of the solar system, including the distribution of smaller bodies like asteroids and comets. The story of Earth's formation is particularly compelling. Initially a molten mass, Earth underwent differentiation, a process in which denser materials sank to form a core while lighter materials rose to create a mantle and crust. This differentiation laid the foundation for geological activity, including plate tectonics and volcanism, which have been critical for shaping the planet's surface and atmosphere over billions of years. Earth's development as a habitable world was profoundly influenced by interactions with other celestial bodies. One significant event was the hypothesized collision with a Mars-sized object early in Earth's history. This impact is believed to have ejected material that eventually coalesced to form the Moon. The Moon has since played a vital role in stabilizing Earth's axial tilt, which affects climate and seasons, as well as influencing ocean tides, which are crucial for certain ecological processes. The presence of water on Earth is another key factor in its habitability. The origin of Earth's water remains a topic of active research, with theories suggesting contributions from both volcanic outgassing and impacts by icy comets and asteroids. Water provided the medium for the complex chemistry that eventually led to the emergence of life. Life, in turn, has profoundly altered Earth's environment, particularly through processes like photosynthesis, which has transformed the atmosphere by producing oxygen. The formation of the solar system also involved the development of smaller bodies, such as asteroids and comets, which are remnants of the early protoplanetary disk. These objects provide valuable insights into the conditions and materials present during the solar system's infancy. For example, the asteroid belt between Mars and Jupiter represents material that never coalesced into a planet, possibly due to the gravitational influence of Jupiter. Similarly, comets, which originate in distant regions like the Kuiper Belt and Oort cloud, contain pristine materials from the outer solar system, offering a glimpse into its primordial state. The dynamics of the solar system have continued to evolve over billions of years. Interactions between planets, moons, and smaller bodies have led to phenomena such as orbital resonances, migrations, and even ejections of objects from the solar system. For instance, the migration of Jupiter and Saturn during the early solar system's history is thought to have influenced the distribution of material in the disk, shaping the sizes and compositions of planets and the asteroid belt. Exploration of the solar system has provided remarkable insights into its formation and evolution. Telescopes have revealed the structure of distant protoplanetary disk around young stars, allowing us to compare these systems with our own. Space probes have visited planets, moons, asteroids, and comets, collecting data that enriches our understanding of their composition, geology, and history. Missions like the Voyager spacecraft, which have traveled beyond the outer planets, continue to expand our knowledge of the solar system's boundaries and its interaction with interstellar space. Theoretical models have also played a crucial role in unraveling the complexities of solar system formation. Simulations of molecular cloud collapse, disk dynamics, and planetary migration help scientists test hypotheses and refine our understanding of the processes that have shaped the solar system. These models, combined with observational data, have revealed the interconnectedness of the solar system's components and their collective evolution. The formation of the solar system is a story of transformation, resilience, and interconnectedness. From the collapse of a molecular cloud to the emergence of a complex system of planets and smaller bodies, each step in this journey reflects the intricate interplay of forces that govern the cosmos. The resilience of celestial bodies in the face of collisions, migrations, and other dynamic events underscores the adaptability of the solar system's architecture. Meanwhile, the interconnectedness of its components, from the stabilizing influence of the Moon on Earth to the role of Jupiter in shaping the asteroid belt, highlights the delicate balance that has enabled the solar system to persist and evolve. As we continue to explore the solar system through telescopes, space probes, and theoretical models, we gain not only a better understanding of its past but also a glimpse into the broader workings of the universe. The study of exoplanetary systems, planets orbiting other stars, has revealed both similarities and differences with our solar system, deepening our appreciation of its uniqueness. By unraveling the mysteries of the solar system's formation, we not only learn about our own origins but also contribute to the broader quest to understand the cosmos, and our place within it. Let us know your thoughts in the comments below. And if you found the video interesting, don't forget to like, share, and subscribe for more exciting content. Thank you for journeying with us here on Frontiers of Infinity.